Two things to update today. One is, as you know, I've been going over the secure multi-party computation zero knowledge proof angle, and so over the last week, I've gone back to the original paper that kicked off this particular line of research. Okay, so this is the initial paper that kicked off the whole this line of research, and you can think of it as they're trying to get a win over the computational complexity by shifting from checking a circuit to checking communication traces in a protocol. Essentially, that's the way to think about it. So they're starting with a secure multi-party protocol, and then they are they're reading off the log of the communications between the parties and using those as proofs. So essentially, they're making a commitment to a particular trace of the protocol, and then the verifier is investigating the trace, and if the trace has certain features, in particular, if the views of each participant in the protocol are consistent, then you can prove to the verifier with the zero knowledge capabilities that the statement that you're trying to construct is in fact true, without revealing anything about how it's true. So one of the things that's really striking is that they don't have in this paper, and this is what's quite interesting about going back to the beginning. They don't have a good language for talking about protocols. They actually characterize the protocols in terms of functions. So I can show you what's really happening. Yeah. So it's in this section where they they assume a next message function. So they have a global view of the protocol rather than a local view of the protocol. Now, arguably, they need that in order to construct their proof, but there's another way to do this. And in fact, the whole machinery would be dramatically improved by rewriting the entire thing from a process algebraic perspective, or process calculus perspective, and using by simulation. In particular, because everything is so functionally oriented, they are unable to see that there are situations where non-determinism will make it impossible to distinguish at the trace level variations in the protocol that make a world of difference in terms of the semantics. So, for example, Milner pointed out even as early as CCS that traces can't distinguish between non-deterministic branching and deterministic branching. So, for example, suppose you have a sum that will do an A action and then a B action, or an A action and then a C action, versus doing an A action and then either doing a B action or a C action. So traces cannot distinguish those two things, but notice that semantically they are quite different. Milner uses the vending machine, the famous vending machine example. So if the vending machine non-deterministically after the quarter, so non-deterministically, it will take a quarter in and then spit out chips, or take a quarter and then spit out chocolate. That's very different than taking in the quarter and then either spitting out chips or chocolate. Right? So you can think about this entirely in terms of the user interface, right? If the non-deterministic choice happens prior to the taking of the quarter, then the experience for the user will be they put in the quarter, and then either the chips button will be grayed out or the chocolate button will be grayed out. Because the choice has been removed from them. Right, the choice happened prior to taking the quarter in, versus taking the quarter in and then the user gets to choose either chips or chocolate. Right, that would be the first one would be a very frustrating user interface for many users, whereas the second is more or less what users expect today out of their vending machines. Does that make sense?
Oh yeah.
Right. Okay, good. So then the thing is that traces cannot detect the difference between those two situations. Right? The traces are exactly the same. It's A followed by B or A followed by C.
Yeah.
But the semantics by simulation can in fact detect the difference between those two. And so the trying to reason about these protocols from a trace level is not ideal. And the only reason they can get away with it is because they have a global view of the entire system. And and the system is expected to behave like a function. So that's really what's going on in this paper, is that they're expecting the protocol to behave like a function. What I'm in the midst of doing now is rewriting this piece of the results in a process algebraic formulation, so that we can kind of test the boundaries. If this doesn't behave like a function, what can you really say? So that's kind of where I am with this research. And now I understand also the other reason that a lot of these researchers want to reduce this to linear algebra, because none of these researchers have a language for writing down protocols. They don't have an algebraic machinery which allows them to manipulate the protocols. So this is again, how do I say? It's the siloing of knowledge, right? So there's one computer science community doing interesting work, but without the tools from another computer science community that would make their lives a lot easier. So that's but this is it's very useful. So essentially, the researchers that are using the matrices, they're using them because it's the only machinery that they've got, and they're just lucky that it also happens to be, have a good complexity characteristics. So that's really, it's a bunch of happy accidents. So that's kind of it's very interesting doing all this spelunking to get at the heart of what's going on. But anyway, so that's the update on the zero knowledge stuff.
I just wanted to ask you in today's session, is there some other way than just using linear algebra for this? And you answered my question.
yeah, exactly. Well, I mean, the advantage of using linear algebra is fantastic, right? Because linear algebra is embarrassingly parallel. Right. That's one of the nice things about it, and that was kind of the point of last week was showing that how much parallelism there is in any kind of linear calculation. And the nice thing is when you express the linear algebra in Rolang, you can see precisely where the parallelism is, or where the opportunities for parallelism are. Yeah. So now, go ahead.
I'm sorry, can I just extend my question?
Yeah, sure.
So I was listening Jim Keller. He's working on Intel, I think. I'm not sure right now, but he's developing like low-level stuff. And he's saying that now in chips, first we implemented linear algebra to speed up, then topological stuff, and after that, what he says for the next for the machine learning. Sorry, I'm missing the word. And I wanted to ask how this compares to your view of with Rolang and how these different types of computation.
Yeah. I understand.
Convolutional as like three different.
Yeah, so I mean, convolutional is actually quite interesting, and I'm still.
I don't know what this means. So.
Yes, it's actually it's worthwhile understanding convolution. We'll maybe take a quick detour. So I'll pull up the Wikipedia page so we can talk about it. Let's see if I can find. Yeah, so here you go. So you have some parameter that you are essentially summing over, but you're summing over tau, which is going to represent some delta from some t, and you're multiplying the two. So you're convolving two functions, say f and g. And you have some parameter that you're summing over. So in this case, it's tau. Can you see this?
Oh yeah, yes.
Okay, so you have some parameter tau, and this integral you can think of as like a kind of sum, and you're convolving over that parameter. And here you're taking f of delta, but g is you're taking t minus or f of tau, and here you're taking g minus the tau, right? So that's a way of doing it. It turns out you get an equivalent definition if you flip where you take the delta, right? But this way of doing it is it can be generalized. So here you have a similar approach, right? So here you're doing the integral over the group members, and so you're doing the group composition. Sorry, no, they're complex valued. So your ordinary multiplication, you have, but it's a group. The functions are sourced at a group, right? Which means that you can do an analogy to the thing that we did up here. But it's more general than that. So let me see if I can find it. Let me see. Let's see. Profunctors are composed using convolution. So let's see if I can find that. This should do the job.
I was reading something about that. Yeah, I remember.
Yeah. So assuming. So again, you have a coend, which is performing the function of your sum or your integral, and then let's see if I can find it. Yeah. Okay, so you take the HOM of C1, C2, and C. So the day convolution. So X is coming from the HOM of C1 to V, and Y is coming from the HOM of of C to V and C to V, and then we're gonna take it to something that lives in that HOM, right? Does that make sense?
Okay.
All right. So then we're gonna look at the HOM from C1 tensor C2 to C, and we're going to compose that, or so I'm trying to figure out what the V tensor is. Oh, I see. And then so we're doing the, because this is V enriched, right? So we can take the V tensor with X of C1 and Y of C2, right? So this is roughly the same notion. You're sort of you're lifting this notion of the convolution up. Now, the important thing is to have a bunch of examples in your toolkit so you can kind of see how all these examples are the same. I'm not prepared to talk about that, but I just wanted you to be aware that, I mean, I can pull them out, but it's just not what I wanted to talk about today. But the what I wanted you to see was that convolution is a very general idea. It's not just restricted to linear algebra. It's a super common pattern that happens across a lot of different domains. So you can kind of get the, you can get the original idea from, yeah, there you go. You can get the idea from the linear algebra point of view.
I see. So this is why he's saying this is like the evolution of different computational models that they are pushing inside the chip. right?
Yeah, that's
More.
yeah, exactly. Yeah,
I see. I see.
this turn. Gosh, there's some really nice ways of thinking about this, but I'm not prepared to talk about this. This will take us way too far.
Yeah, I don't want to move you from your topic.
Yeah.
Thanks.
Sure. Okay, so we have some interesting developments over on the proof theory front. So it turns out that it's just easier when dealing with the negation that is based on the collection as opposed to the negation that's based on the execution, that we just simply restrict ourselves to an intuitionistic logic. So here, what we've done is we've gotten rid of the or and replaced it with a product. But the reality is that the product is, because you have exchange and you have contraction, this product is really giving you finite sets. So the witnesses will all be sequences, but because you've got the ability to flip things around in the sequence and to contract any duplicates, these will always be basically finite sets. Does that make sense? Do you understand what I'm saying?
So this means there cannot be par inside negation, or
well, again, remember, there are two kinds of negation here. One is a negation that's related to your collection. So that's where your logical operators live. And then there's a negation that's related to your term operators. For convenience, just to get the ideas across, we've restricted the collection stuff to just be what is easily and readily modeled with an intuitionistic logic. And that's going to be, so essentially what we're building is a linear, nonlinear situation where the linear stuff is not related to the nonlinear stuff in the usual way. So the linear stuff is coming because you have this K operator, which is a, at the head of a rewrite rule, right? So K is going to be like application or par or whatever, right? And then you deny, and then you resource K. So in order for K to actually take a step, it has to have gas or flow or something, right? And so if you deny the resource, then K becomes something like a tensor. And so that's what all of this stuff is here to the right of that. Now, the interesting thing is that when we do that, so this becomes just term constructors. And when we introduce collections and the arrow types, and there are two different arrow types, then we have to keep them somewhat separate. So you have to how do I explain this? You can see it in the mathematical construction. There's no sigma in this line in the grammar. So here we're only building up terms. Here we build up the term constructors over the sigma. Here we build up the term constructors over the arrows. And here we build up the term constructors over the linear arrows. Does that make sense?
Yes.
Okay. All right.
Can you please expand the view to be a little bigger?
Yeah, sure.
Oh yeah.
So the grammar looks a lot more complicated than it actually is. What we've done is a kind of two-level type decomposition, but we're not fully tying the recursive knot, right? So each one of these is the same addition, but it's like term constructors over collections, term constructors over arrows, and term constructors over the linear arrows. That's essentially. And so what I've got to do now is to clean up all of these so that they don't mention taus, but they mention sigmas, and then similarly here. So there'll be kind of a, you know, so that these are not just in terms of taus. Like before, the types were, we tied the recursive knot. And here, what we're doing is we're leaving it only half tied. Only one of your shoelaces is tied. So that's an interesting point, is that we're keeping them separate, at least for the time being, because this stratification, this stratification ends up being technically convenient, I think, is the best way to describe it. So that's kind of where, that's the update on this work, is that we've gotten rid of the classical set constructions, moved it to what are effectively finite sets, and even though they look ordered, they're not ordered because of the exchange rule. So, for example, just to be clear about that, here's the exchange rule, and here is the contraction rule. So if gamma together with delta thinks that x is of type tau1 and y is of type tau2. So if this context thinks that t is of type tau, then this context in which we flipped y, oh shoot, that's a typo. It should be y and x. Let me fix that right now. I'll just do that real quick. You can see there's tons of.
But isn't that tau2 is now in the first place? So it seems correct.
No, but it should be a y.
Oh, I see. So this means that the context gamma, inside the context gamma, there is no order, right?
Right. Exactly. Inside the context, there's no order. So there we go. There we go. That's better. Let me do /math.sf and this thing here. That's weird. Okay. All right. No. Here we go. Okay, there we go. So there's exchange and contraction. So even though we're forming these lists, and we have projections, the fact that you can swap means that these really are unordered, and the fact that you can shrink means that if you have duplicates, they can be gotten rid of. Yeah, so that's why it's reasonable to say that this is in fact giving you finite sets. But the important thing is that this is what's provided. Oh, sorry, up to here. It's a little bit tricky. So I'll go up here. It's easier to see it that way. Here we go, right here. Okay, so this is what's provided by the Levier theory. This is what's provided by the rewrites. All right, so this is our input. Okay. And then when we add the resourcing, we're simply saying that, you know, K is not allowed to, without an R, you don't have a rewrite. So the source of rho is not a K anymore, but an RK. All right. And then F hat decides what you do with the resource. So if you consume the resource, it's linear. If you leave it alone, then it has no effect. And if you add more resource, then it's wildly nonlinear. Right. So that's what the F hat is doing, right? It's saying what happens. It's not only saying what F does with T and U, but it's saying what happens to the resource. So that's the, so this is the, here's what we're given. Here's the first step in the introduction, right? So we do the resource because you can't make a rewrite step without the resource. You can now ask for accessors to get at the T and the U, and that's what these are. They're not straight up accessors. This is going to allow you to access them in parallel, and this is going to allow you to access them in series. That's sort of what these two are. So these are two different forms of par. And then the higher order algebraic theory is giving us one kind of arrow. Right, it's giving us a lambda style arrow, right? It's forming a context, and then the linear is the linear arrow is insisting on certain kinds of contexts, right? So contexts that have R's in them that are also constrained in terms of how the terms may evolve, right? So they don't get to evolve willy-nilly. They have to evolve within a particular constraint. So that's and these arrows are in fact not. Initially, we had been thinking that if you take an arrow like this and you follow it by a one-step. So one of these things here. So if you do circle 1 tau, so that tau arrow circle 1 tau prime is the same as tau lollipop tau prime. Spiritually, perhaps they are akin, but they're not exactly the same because this insists that there's an R here, which is not guaranteed by the other arrow. Yeah. So they're closely related, but they are in fact not the same. But anyway, so the point is that this stuff, skip over these two, and that are what you're given. When you throw in the resourcing, then you get the rest of it. So this is all just term structure and not, it doesn't deal with any of the higher order stuff. Since we know we're dealing with collections, so those collections again we're not given we're not given this in terms of this theory, but because it's an HOAT, we can still form these collections. So we have a right to form that, but we have to distinguish the collection types from the sort of pure term types. And then again, because it's an HOAT, we can form these arrow types, right? That's what these lambdas are here, but they're not a part of the term language, so we can't mix them. And then similarly, because of all the structure that we've delineated above, we have these arrow types, but they are not term types. We have these lollipop types, but they are not term types. So we have to disambiguate them. So that's essentially what's driving this level of delineation. It also brings up an interesting point, which is that while there are data definition languages, there are plenty of data definition languages that allow for a variable on the left-hand side of your definition symbol. Grammars do not. There's no theory of grammars that allow you to talk about a variable in the head of the grammar, in the non-terminal symbol. So that would be, it's like we know what it means because they're all the data definition languages from Java from C++ to Haskell have the ability to take a variable in the non-terminal symbol. So it would be really great to have even these abstract grammars have this capability.
Yeah.
Right.
This is basically like a parametric, polymorphic definition, right?
Polymorphic grammars. Yeah, exactly.
Yeah.
Right. So that's and it makes a ton of sense, right? Because this would be a way to then you wouldn't have a hard, fast line between lexing and recognizing terms, right? So you could use a grammar to define your lexer, right? And you could have in levels, right? So the n minus 1th level is the lexer for the nth level, right? So that would have dramatically improved the lives of those who are working in complex event processing, because they could talk about aggregating at another level and aggregating at another level in terms of grammars. But it was
yeah. And this is exactly what I was thinking for definition of the protocols. For example, in protobuf, you also don't have this, and you need to
exactly. Exactly. It would be very, very nice to have this feature and capability. And I'm surprised that we've had 60 years of this stuff that it hasn't been properly treated. So it's perfect to find some assistant professor somewhere and give it'd be a perfect career. Anyway, that's the updates on this stuff. It's sad to me that it makes it look complicated, because it isn't complicated. It's just that we have to stratify it in this way. So I'm gonna see if I can find a way to if I had variables on the left hand side, then I can write it in terms of a composition of grammars, but here I can't write it as a composition of grammars, right? But that's an interesting exercise, assuming that this was a data definition language instead of a grammar. Can you write down this structure as a composition of grammars, or a composition of data types?
Greg, you mentioned HOAT.
Yeah, higher order algebraic theories.
Okay.
So the higher order algebraic theories are, let's see, let me grab it.
It's directly related to higher order abstract syntax.
Yes.
Not?
Yeah, it is.
Okay.
So higher order algebraic theory. Probably this one. Can't remember which one is that. No, that's not it. Never mind. Well, I mean, Fiore is the guy who did it, right? So his slides are fine. Let's see if he does the notation. Yeah, so this has got the nice notation. Yeah, exactly. So he's got two contexts, right? So you've got yeah, so your context has more structure. And you're allowed to now talk about terms with holes, right? So there's an example of a signature for lambda calculus, and then he defines substitution. At this level. So this is a yeah, there you go. So you have substitution and meta substitution, and so it's quite pleasant. I mean, it's more notational machinery than just lambda, but it's kind of the minimal notational machinery you need if you want to have the general accounting of binders like lambda or input in the row or pi calculus. So that's what, when I say higher order algebraic theories, this is what I'm talking about. It's you can think about it as a Levier theory with some exponentials, not necessarily all exponentials. You've got some exponentials. That's a way to think about it. All right.
Okay.
That's the update for today. Hopefully we'll have both of these things cleaned up, right? So I'll have the paper cleaned up so that we have all the inference rules, and then cleaned up that way, and then we'll start working on more examples. It was actually working through some of the examples that we realized we wanted to clean up. Sorry, so we were working on the prime examples, and so we realized we wanted to clean up the collection stuff, and when we cleaned up the collection stuff, we realized we had to clean up the other stuff as well. Any questions? It's good to see you here, Steve. Steve Ross Talbot. So, unlike you to join the Casper Standup.
Well, I thought I'd challenge myself today. I'm going to lie down after this.
Oh, good for you. Well, hopefully you're getting over your cold.
Yeah, no, I'm okay now. I've still got a bit of a cold, but it's not as debilitating as it was. So
yeah. My trick is to, as soon as I have any symptoms at all, anything noticeable at all, I go take a nap. Like I was starting to feel a bit of scratchiness in my throat yesterday, so went and laid down and got some rest, and then it was gone. No symptoms today. Yeah. All right. Well, thank you all so much, and we will. I'll see many of you on the Dev Stand Up in a little bit.
Thanks, Greg.
Sure. Thank you.